I want to come some success story when introducing the bioplastic in Italy. What happened is, before to address the plastic, what they found, they collected the waste. They went to the marine environment, they collected the plastic waste. Out of the collected waste, they found that 41% is a plastic carrier bag. So the government, what we decided, before we go to ban the plastic bag, let us have a solution. Whether we have a technology to address that issue. That's a clever idea. Before you are banning and everything, because the packaging is very important. You cannot have a without protecting, meat protecting, packaging playing an important role. So what they done it, they have a technology. They found the right technology with a certified European 13432. So they found that there is no options of heavy metals and the biodegradability within 6 months, and negative impacts after composting. There is no negative, and also the technology is biodegradable in soil and marine environment. They have certified everything. Then they put the law to ban the single use. So what it happened is, they banned it in 2011. It's the lightweight material, traditional, the thin film, all the they banned it. So it created a positive effects. So they started to increase the reusable bags and use of first biodegradable compostable bags and the bio-waste bags with more environmental awareness. And they introduced a new organic waste bin. So you can collect the food waste, whatever, together, you can put this bio-waste bin and everything. You can put it. So 94 Italian supports this technology. And almost in Italy, almost 40 million pack make the separate collection of organic waste. They have a separate system. And what they found, the quality of organic waste collected, it was almost 96% purity. Earlier, there was a contaminating the composting, but the organic waste collected, they have a 96%, and 5 million tons they produced per year, and the capture rate per person 90 kg per year. This was a success story. So what is happened it is reflected in the economy, bioeconomy as well. So there's a new value chain created. It means that currently their aquaculture business was declining, but this one, they started to use the aquaculture biomass to create a new value products, high value product like a biomaterial. So it created a new jobs and in local production, and also started local production using the local biomass products, and they give opportunity to the traditional plastic companies to apply the plastic transformation to the industry. So give opportunity, and also boost for local growth areas. Particularly, the company was declining, some of the agriculture biomass company. So there is a new opportunity they found. They started promoting that agriculture biomass, and also for the different application. They made a new investment in the R&D. They want to use for different application, cutleries and other packaging, barrier film, so many applications. There's also new job opportunities created. And this one represents a model for new regulation and environmental field. So that helps what you have to do in the environment, how to protect the environment, what kind of law, what kind of policy we need to create. That helps. So that is we need. That based on that concept, the CSIR also want to follow. But when you go for bioplastic, are we having enough biomass to develop a bioplastic? And one of the studies we had done it together with the Department of Science and Innovation and our Waste Roadmap program, and we found that we have an enormous agricultural biomass. It's not been potentially utilized. It's still underutilized. That we can develop a bioplastic technology. You can use paper, pulp waste stream, sugarcane, maize, chicory, pineapple, other high-value products. This industry already under stress. You can use the raw material to develop the bioplastics. And how to, so you can use the different, so you can use, these are, you can use the different sugarcane, bagasse, maize stalk, and waste. So these are, you can differentiate the high price and low cost. So you can, from that, you can take it to biorefinery. This is the initiative, the CSIR initiated, the CSIR DST Biorefinery Center. So you're extracting the value chemicals like cellulose, starch, and other biochemicals. Then we are developing like a from that biomaterials. Currently, what we are doing, there is sugarcane bagasse, what they're using for bioenergy or biofuel. So what we are doing is we are identifying the low value agriculture biomass. I want to create a high value materials. That's the CSR research going on. So we are utilizing specifically the sugarcane and maize byproducts. We are trying to extract cellulose, starch, hemicellulose, lignin, and we are trying to manufacture it using material in the bioplastic. So when you design the bioplastic, always we are keeping in mind that materials should be reusable and recyclable, and if it reaches end of life, it should be completely biodegradable. That is the research R&D we are currently focusing in. So we actually, our research group is mainly focusing on particularly in the bioplastic formulation. So we are mixing the biomaterial compounds different, like a starch, cellulose, chachinic acid, lactis, and trying to make using the conventional machineries. We are trying to use the extruder, so like a single screw extruder, twin screw extruder. We're using all the ingredients and we make a pellets. That pellets, we developed as a bioplastic formulation that you can use for any rigid packaging as well as the flexible packaging. And that is R&D, the CSR's focus. So we identified there is a potential products from that the CSR R&D we can use for cutleries, the sanitary barrier films and crates. We can carry it back, and particularly mulch film. One of the very important role the biodegradable is going to play a major role in the agriculture mulch film. So after harvesting, you no need to collect. It degrades directly in the soil and give organic content to the soil. So it enrich the soil quality. That is advantage. So you no need to, currently after harvesting you have to collect the waste and put into the landfill and everything. So this kind of advantage. It has a niche application, particularly the nursery. Then you can have when the plant grows, the material soil will be degrade. So that is advantage. Also, what we found that what we developed the technology, it has a good mechanical properties that's similar like a polyethylene, polypropylene materials. So and also it can be used in the conventional extruder, blown film, single screw blown film extruder, and extruder. You can use the same injection molding technology. What we found also, the developed technology is 100% biodegradable in soil, compost, and water, and also 100% mechanically recyclable, and is a renewable resource and is non-toxic, and also is suitable for packaging application and all mulch film and other application that also we found. So this is one of the very important. So when I design the material, I have to scientifically prove my material is completely biodegradable and everything. So we have a biodegradation testing facility. So we tested in compost, marine water, and everything. So we found that this is so what we are measuring is it's not like we are actually mixing the microbes eating the plastic carbon and gives the end product like a CO2 and water. That we are measuring. That is called the mineralization. That we are testing it. It's not just like a fragmentation, the degradation. We are seeing the final end product. That is we need it. That is 100% biodegradable. So and we scientifically finding what are the role of microorganisms degrading. This is some of the evidence that is the technology is degrading the marine water as well. You can see 140 days there is no plastic, completely soluble. The advantage of that the bioplastic. The first process is called primary degradation. So the microbes is eating on the plastics and surfaces, try to break in the long chain into smaller. So when you break into smaller chain, the microbes is a low molecular weight. You can easily assimilate it. So the idea is when you're reaching if your materials degrade, if it reaches the marine water or soil, so the raw molecule is degrading. That is a interesting research we found. So this test in the soil condition, we found after 90 days completely biodegradable. So what we found also very important is if you have a different environments like a compost, soil, freshwater, marine water, where is the highest degradation happening, particularly in the compost. So if you have an industrial compost, they usually operate it in a 58 to 60 degrees Celsius. So the temperature is a playing role, and also the specific microorganism, bacteria, thermophilic bacteria and fungi is playing a major role. So it can degrade very quickly. Within 3 months in industrial compost it can degrade. But if we put in home compost, it takes maximum 6 months it can degrade in compost, home compost, in soil. And also we found that the marine water also is degrading within 6 months. So this is we found that highest degradation we found in the compost. So our recommendation is, so you should have a closed system that you can first put in the compost, they can control, that can, if then if you don't mistakenly, if it reaches the landfill, still is going to be degrade. Then if it even reaches the ocean, then it's going to be better. So that kind of approach, it is going to help the plastic pollution issues. So our recommendation is, the trend of plastic production, consumption and the environmental concern, the plastic is favor of increasing acceptance. The biodegradable plastic is increasing acceptance in many countries. So that will helps to address the plastic pollution issues. But if you're utilizing the agriculture waste byproducts and everything through the R&D of biomaterial formulation, by renewable, recyclable and reusable opportunity, there's a creating a new biomaterials you can use for many applications, including packaging. And also from using the renewable resource, can be developed a cost-effective feedstock for the production of biodegradable plastic products. And also the biodegradable plastic, wherever we see that there is plastic is not economically viable, and so still the biodegradable plastics, it can be replaced, that kind of items. And also particularly the non-food organism, non-food feedstock, particularly not necessarily to be used corn directly from the starch and everything. So you can still use the non-food crops to develop that one. So that is going to be the future of the technology to address particularly the environmental concern regarding the plastic waste and the economic challenges. Also, I like to acknowledge the support to NRF and the Department of Environmentalists and the Department of Science and Innovation R&D Waste and Roadmap, and also Department of Science and Innovation Bioeconomic and the CSIR. Also, I'd like to thank the industrial partners. When you develop a technology, the industrial partners playing a major role, because we are researchers, we work in the laboratory, but the industry people knows more about when you develop a technology, they know what to do, when the production goes. So I like to thank the Hendros Plastic and the RV Packaging. They helped a lot. They worked with us last 3 years and helping, and how the industry works, what need to be addressed, everything. They help a lot to some of the proof of concept to be developed. They help a lot. And also I like to some international collaboration. University Pisa, Tianjin University, IIT Chennai, Allahabad University, University of Gulf, they have collaborated this project and supported this project to recommend some process. Thank you.